Let's talk a little bit about the greenhouse effect, which is another important influence on Earth's climate. To understand the greenhouse effect, we have to know something about what electromagnetic radiation is. That is any type of radiation which involves electromagnetic forces, which involves photons, if you've learned about those in physics. And it includes visible light that you can see. It includes ultraviolet radiation that you can't see, but that can affect chemical bonds. And, we put on sunscreen to protect against UV damage to our DNA. It involves infrared light, aka heat radiation. So if you can feel heat coming off of a heat lamp or of hot asphalt or of a person, that is actually infrared radiation, which is very similar to visible light, except that its wavelength is different. That's the main difference in between all of this light, that there's a change in the wavelength, which corresponds to an inverse change in the energy. When waves are far apart and the wavelength is long, so this would be the wavelength here of this light, we have fairly low energy. Big wavelength, means low energy. Whereas if we have a very small wavelength, that corresponds to high energies. Think about the vibrations of those electromagnetic waves going back and forth much more frequently as corresponding to an increase in energy. And we can see that there's UV radiation, infrared radiation, and visible light all fit into that spectrum. Visible light is actually this teeny tiny part of that whole spectrum. And then there are other things too that are included in there: X-rays, gamma rays, radio waves. Microwaves are a part of that, that sometimes we break out and put in this area here. Those are all classes of electromagnetic radiation, and that's the type of radiation that reaches us from the sun and that also leaves Earth as a result of Earth warming up and releasing radiation. That's all electromagnetic radiation that we're talking about. The greenhouse effect refers to the effect of gases which can absorb some of that radiation. So many gases let visible light pass through. That's why we can see all the way up to the stars at night, why we can see the sun during the day. So the huge volume of atmosphere above us and the gases that make it up let a lot of that visible light that we can see pass through. But some of those gases absorb infrared light at a lower energy, at a higher wavelength. That constitutes what we know as radiated heat. The gases can absorb infrared light when their vibrations, diagrammed below, match the frequency of that infrared light. So these molecules, like carbon dioxide and water vapor, shake back and forth with characteristic frequencies, numbers of times that these vibrations go on any given second. When the frequencies of those vibrations match the frequencies of infrared light, those molecules can absorb that light as it passes. And that light that they can absorb is always going to be infrared light or heat radiation. And we can see some of the vibrations that contribute to this absorption in carbon dioxide and water below. So there are a few different ways that these molecules can vibrate back and forth, and each of these absorbs a different wavelength of infrared light. The details of which vibrations absorb which light, we're not going to care about. It means that certain gases are going to have what we call certain global warming potentials. They can absorb different amounts of that infrared radiation. And we base it based on carbon dioxide, which we just pin to having a global warming potential of 1. And we base all the other gases off of its ability to absorb infrared radiation due to its vibrations relative to carbon dioxide. So methane, CH4, has a global warming potential of 21, can absorb about 21 times as much infrared radiation as carbon dioxide can. Other gases can absorb more, but they're just lower concentrations in our atmosphere, like nitrous oxide can absorb over 300 times as much. CFCs, some of those ozone-destroying gases, which isn't totally connected to climate change, but if we have a little bit of CFCs in the atmosphere, that can influence it. Those can be 6,000 to 7,000 times the global warming potential, that is the infrared absorption ability of carbon dioxide. and a bunch of other chemicals too, like sulfur hexafluoride, 24,000 times as much. I'll note on here that we don't have H2O pictured. H2O, water vapor, is also a potent greenhouse gas, but it enters and exits the atmosphere so frequently that we treat it a little differently than we treat these other gases, which tend to be fairly long-lived in Earth's atmosphere. So we need to think about it in a different way. Remember, if you've seen the lecture already on the hydrologic cycle and on reservoirs and fluxes, we did a quick calculation and found that water vapor on average stays in the atmosphere about 10 days. So it's not up there nearly as long as CO2 or methane, which can be up there for hundreds of years or more. All of these gases, CO2, CH4, H2O, are some of the biggest contributors because they're so common in our atmosphere. These gases can absorb both incoming and outgoing infrared radiation. And so we can diagram what the sunlight reaching the top of the atmosphere looks like in red, or excuse me, in yellow there. And then in red here, with these bites included, this shows the radiation that actually reaches us at sea level. Part of that difference is going to be due to scattering, reflecting back, but part of it is due to absorption of infrared light by certain gases, and we've diagrammed some of them here. So this big bite out of the radiation here is due to water vapor. This big bite here is due to water vapor. This big bite here is due to water vapor. Some of these little bites down here are due to carbon dioxide. They have a particular wavelength of light, and that wavelength is going to, in some way that we won't talk about mathematically, translate to a frequency of vibration of those molecules. Those big bites are where the molecules match the frequency of vibration of the electromagnetic radiation and can absorb it. One more time, some sunlight is going to reach Earth's atmosphere in yellow, but it gets filtered out, and what reaches us at sea level in red is less than that because of the greenhouse effect, because certain gases absorb radiation. Now, this is the radiation emitted by Earth. This is what we would emit just based on our average temperature in this curve right here. And so the big bites that are taken out of this are radiation that would otherwise leave to space and cool Earth because it's leaving, but instead got absorbed by certain gases, by CO2, by ozone, by methane, by water. Because of these big bites, Earth is not losing as much radiation as it otherwise would. So when the greenhouse gases are absorbing that radiation that otherwise would leave, they eventually have to re-emit it because that energy can't be destroyed. Some of that energy is emitted downward, some is emitted upward, but some is emitted downward, which ends up warming Earth. So you can think about the greenhouse effects in two ways. You can think that it slows down the radiation that's leaving, or you can think about those gases absorbing that radiation and emitting it back down toward Earth. Those are really equivalent ways to think about this. The moral of the story is that greenhouse gases in our atmosphere trap some of that infrared radiation and cause Earth to warm up over how warm it otherwise would be, just based on the sun. Now we can go back and look at this diagram and think about why it is that different planets, Mars a little bit, Earth a little more so, and Venus especially, why their true temperatures are so much higher than the temperatures that would happen just from sunlight. This is due to the greenhouse effect, due to the greenhouse gases in those atmospheres. These cause these planets to trap a lot more of that infrared radiation than they otherwise would. And as a result, they have to heat, the planets have to heat up more to emit a correct amount of radiation to balance what comes in and what goes out. The greenhouse effect warms Mars by only about 6 Celsius. Its atmosphere is mostly CO2, but it's a very thin atmosphere, so it doesn't have a ton of impact. The greenhouse effect, including CO2 and water vapor especially, warms Earth by 59 Fahrenheit or 33 Celsius. A lot of Earth would be pretty frozen without any greenhouse gases at all. These greenhouse gases warm Venus by a whopping 905 Fahrenheit or 500 Celsius. Just a crazy amount they warm Venus. And that's because not only is Venus's atmosphere all carbon dioxide, but it's very dense. It's so much more dense than our atmosphere. It's 93 times as dense as our atmosphere is. So there's a lot of CO2 in Venus's atmosphere. And that means the greenhouse effect is huge on Venus, pretty substantial on Earth too. Now, I'll mention that these Milankovitch cycles that we've seen, the sort of up and down variation that's due to Earth's orbital variations, turns out they're also well correlated with carbon dioxide, which can be confusing because those Milankovitch cycles are dependent on Earth's orbit. CO2 is definitely not directly dependent on Earth's orbit, but they're both influencing the temperature. It turns out the reason for this is that there's a feedback. Things like colder oceans, as you cool off temperatures, those colder oceans can absorb more CO2, which is going to further lower the temperature because there's less CO2 in the atmosphere. And so as a result, when temperatures go down, CO2 levels start to go down because the oceans start to absorb that carbon dioxide. There's what we call a feedback. And that feedback is kind of similar where we talked about the ice sheets growing and as a result reflecting more life and cooling off even more. That's also a feedback. Turns out climate science is littered with these feedbacks where warming can cause more warming, or warming can cause cooling, or cooling can cause warming, or cooling can cause further cooling. And we'll talk a lot about those in a future lecture. But I want to point out here that there's some relationship where carbon dioxide not only depends on the temperature, it also influences the temperature. Stuff gets pretty complicated. Now, is the greenhouse effect like a greenhouse? Sort of, not really though, because a greenhouse, the way that it works is that by closing all of these doors and windows, you can let visible light in, and then the air warms up, but the warm air cannot leave. So the greenhouse is really working because it traps warm air. Whereas greenhouse gases aren't trapping air, they're not trapping gases. Those gases are trapping radiation. So I just want to point that out so that folks don't think these work in exactly the same way. It's sort of a greenhouse effect because it's trapping heat, but they trap heat in different ways. All right, folks, thanks for listening to this lecture. We'll see you next time.